presentation, I would like to introduce Flint Hughes. So he is going to be sharing with us his work relating to the standing scale patterns, dynamic impacts, and prospects of ROD for management. So Dr. Flint Hughes is the research ecologist for the U.S. Forest Service Institute of Pacific Islands Forestry here in Hilo. Flint is one of our leading scientists for the project and has been here since the beginning. Flint's recent research has been taking a look at ohia plots across Hawaii Island, and he'll be sharing some of his research findings with all of us. So I look forward to his presentation. Thank you, Flint, for joining us, and take it away.
Cool. Thanks so much, Hoku. I appreciate it, and I really appreciate the opportunity to talk with you all today and share what we're learning, and in hopes that it can help you. Yeah. So my name's Flint, and I've been living and working on the Big Island for about 25 years. My wife and I live in Hilo. We have a blended family. She is a attorney, public defender for most of her career, and private attorney. Now we have 4 children. One that lives in New York, one that's our daughter is a firefighter here in Hilo, and then another daughter is college, and another daughter in high school. So that's kind of us. And so today I'm really happy to share kind of a different perspective on rapid ohia death than what Ryan just shared. And I'm always impressed and interested to listen to Ryan and hear what he's learning. And I think it's kind of a great example of how folks have gone about understanding the problem of rapid ohia death and looking at it from a lot of different angles, which makes kind of builds on itself, and it makes our understanding that much richer and that much more robust, and adds a lot of certainty to the things that we're looking at, because we can confirm what we're learning, say on the ground, with what Ryan's learning from his remote sensing work, and from the genetic work, and from the pathology work. And so it's really important, and it's really, I mean, when you step back and you think about how we've worked on rapid ohia death over the years, it's actually pretty impressive to think about the different ways that folks have looked at this. And so
Flint, you seem to be muted.
Sorry, have I been muted the whole time?
No, you haven't.
No,
sorry.
just
okay.
I hit the wrong button. Sorry.
Okay.
Flint.
No, that's okay. Was I just muted for a few seconds then? Okay, yes. Cool. All right, awesome. So like I said, what I'm going to share with you today is about our mortality network and what we've been learning about that over the last 4 years or so of the work, and really just to give you a little bit of background of why I'm doing this work. I have a deep appreciation and value and love for ohia as a tree, and not as value as a timber species, as a commodity, or even as something and individuals that provide an ecosystem service to humans. But I really value ohia for itself, its intrinsic value as a fellow creature that we should help care for and respect. And so that's kind of where I come from in terms of my research. And I just wanted to share that because I think sometimes folks think about how scientists conduct their research and the why behind it. And so I just wanted to share how I feel about my work. And I imagine other people share the same outlook about ohia in particular. So just wanted to express that. Let's see, how do I need to advance? There we go. One last thing before I get talking about our work. I just wanted to give a shout out to all of the members of our Rod Squad team that have been doing this work over the years. And most of what I'll be talking about is derived directly from all their hard work in the field. And so that's those are the names of the folks who've been with us over the years, and they've changed over the years, but they've all been great in terms of the work, hard work and dedicated effort that they've put into helping us understand what's going on. I also want to acknowledge and thank our funding and our collaborators, key collaborators on this work as well. So thanks for that. Okay, so OHIA is important. And I just wanted to point out some features why it's so important to all of us. It's by far the most abundant tree across Hawaii. You all probably know that quite well. It's also, when you look at our watersheds and OHIA's distribution, OHIA forests really define our watersheds. I mean, they're almost one and the same. And so where we have healthy watersheds or healthy forests, we can be pretty assured that we'll have healthy watersheds as well. I mean, that's been the status quo for centuries. And so degradation of OHIA forest runs the risk of really degrading our watersheds and the clean, abundant water that they provide. So that's something to really be mindful about. So there's the water issue. In addition, as probably we all know pretty well, OHIA is very abundant across the islands, especially in the uplands. It accounts for, on the Big Island alone, it accounts for a third of every single tree that exists on the island of Hawaii. And even more so, it accounts for over half of all the forest carbon mass. So when we're thinking about water, we're thinking about carbon. The main story, the headliner across most of the islands, certainly on the Big Island, is OHIA. And so just want to point that out and make that clear. As we've been discussing over the past 5-6 years, we've been studying rapid OHIA death and trying to understand the patterns, dynamics, and spread. This is an image from Greg Applett from Arizona State University, who's been doing a lot of landscape scale work along with Ryan, looking at the patterns and dynamics of spread. This is the image on the left is a 2017 image of, and the yellow shows where OHIA brown trees are across the landscape. And if you look at the 29 photo image, you can see where it's expanding. We really didn't have quite as much mortality in this area as we have here. We also didn't have as much mortality in these upland areas on the windward side as we have now in 2019. And so this is just to show you kind of the pattern of rapid OHIA death development and spread over time. And unfortunately, we're seeing that continue as years go by. And we've kind of done some back of the envelope calculations to estimate about 200,000 trees are dying per year. And that's probably likely to continue over time, unfortunately. So this just to give you a ground view of what we see when rapid OHIA death really takes hold in a stand. This is down Pu'ukaliu, one of the first places to get hit by rod. That's what it looked like in 2005. This is what it looks like in 2015. And this is a photo series that JB put together, which is a great illustration of how devastating the disease can be in areas where it really takes hold and kills trees. So So what we really wanted to look at, and again, it's a great companion to the work that Ryan's been doing, is set up a network of plots on the ground where we have noted tree mortality, and where we were able to diagnose whether it's Ceratocystis leucohea, Ceratocystis huliohea, or something else, where Ceratocystis is present or not, and follow those forest plots over time to look at what happens in them, and start to try to get an understanding based on their individual characteristics and looking at them collectively to see what kind of patterns and what kind of forces are at work that may be affecting whether or not Ceratocystis is killing trees in those given areas or not. So this just a little kind of working person's view of how these plots work. The schematic on the left shows when we first go in and establish a plot, and we're counting live trees, dead trees, we're measuring them. We're measuring the other species in the plots as well. We're looking at seedling regeneration in the plots. And we do that when we first establish a plot, and then every year afterwards, I guess now we have plots that have been bred about 4 or 5 times, I think. We'll go back and remeasure and say, okay, well, now how many dead trees do we have? And from that, we can determine annual rates of mortality for an individual plot, and we can average those to look at them in any different combinations of environmental factors, soil conditions, et cetera, to try to, again, look at these patterns. So that's what we've been doing. From that work, one of the big take-home messages that we've been able to see is we've calculated annual rates of mortality in areas where we know leucohea is present and killing trees, where huliohea is present and has killed trees. And then we have a large pool of plots, like we were talking about before, where we saw tree mortality, but we never found Ceratocystis of either species present. And so what we're able to do is pool those plots into those 3 categories, and then look at, okay, well, what's the average annual mortality? And so what we see is that where we have leucohea, annual rates of mortality, whether you're looking at individual trees in terms of stem count or kind of the size of trees, the overall basal area of the plot, the mortality rate is about 10% per year in areas where we initially had leucohea present. And when we go back and see dead trees in those plots, more often than not, we see that they've died from leucohea. We sample them, yes, they're positive for leucohea, and we're confirming that. What's interesting is in looking at huliohea, those rates of mortality are much lower. They're about 3%, and they don't differ from significantly from the annual mortality of plots where we have neither Ceratocystis species present. That it's just this other mortality effect going on, and that's about less than 2% for if we're looking at a stem count, and maybe getting closer to 1% if we're looking at mortality based on basal area. So that our background without leucohea is quite a bit lower, substantially lower, significantly lower than what we see with leucohea. So 10% is a good take-home number when we think about mortality coming from leucohea, and that really kind of confirms and agrees with those values that Ryan was talking about, those curves, mortality curves. I'm not sure if he mentioned it, but he was calculating that if those curves continue through time, in about 20 years, you'll have complete stand mortality of ohia. And same thing with these values. 10% annual mortality more or less runs out to be complete stand mortality in about 20 years as well. So those values are kind of coming together in terms of the work on the ground and the work that Ryan's doing. One thing to note that there are quite large variations in mortality, even within stands where leukohea is present, even within that kind of overall 10% pool. And I'll be talking more, I think almost exclusively about leukohea infected stands from this point on. So in young stands, they seem to have much lower, well, they don't seem to, they exhibit much lower rates of mortality. So if you are a young ohia stand developing on, say, young lava or reestablishing and some other kind of, after some kind of disturbance, your mortality rates are going to be much lower as a group than stands that have larger individuals growing on older substrate. And again, that's true for stem count mortality or basal area, overall basal area mortality. And those differences are significant. Similarly, we look closely at, we kind of parsed out areas on young lava flows on Kilauea substrates and Mauna Loa substrates, and compared those with the older surrounding substrates. And same thing, we found that on these younger substrates, the incidence of mortality, the annual rates of mortality is much lower. It's about a third of what we see in the older lavas. So if you're an ohia tree and you're on these younger flows, you're much less likely to die from ceratocystis. And we see that when we look at a whole wide variety of lava flows across these two volcanoes. And I know that's maybe not as important on the other islands, but it's certainly a pattern that we're seeing here. So just want to look at some other environmental variables to give you guys an idea about the patterns that we're seeing. And Amber, I can see you really well. Can you give me a shout out when I'm getting really close to being at the end of my talk, just so I can keep track?
Yeah, if you can wrap it up maybe in a few more minutes, and then we'll have some time for questions.
Okay, cool.
Yes.
All right. So just want to point out some things. This shows the variation in mortality among the plots where leukohea is killing trees. So this is, again, leukohea infected plots. What we see is mortality rates decrease with increasing elevation. Okay, that's one thing to keep in mind. We're also seeing mortality rates increase with temperature. So that's kind of a mirror image of the two. So if you're up high, if you're an ohia tree up high, higher elevation, cooler temperatures, your incidence of mortality at the stand level is much lower. Warm and wet, if you're living in warm and wet areas, your incidence of mortality as an overall stand is much higher. So we're seeing increasing mortality rates with increasing annual rainfall. I'm not going to get into the ET, but it kind of follows the pattern with rainfall and temperature for that matter. Real quick, thinking about recruitment and basically, are there ohia seeds in these plots, seedlings in these plots? What kind of recruitment? Well, unfortunately, in the vast majority of these plots, 80%, we have absolutely no ohia recruitment. So we're not finding seedlings or saplings at all in these plots. We see a few seedlings in 5% of the plots, and we see many seedlings, and that's still, many is kind of a small number as it is in about 15% of the plots. So we're not seeing a lot of recruitment, unfortunately, in these areas. And part of the reason is, well, we see most of the seedling recruitment in these upper elevations, and one of the reasons we think that's true is the high coverage of weed species in the lowlands that's really hinders ohia recruitment. This is a good example, strawberry guava infested area in Waukeleopuna. So as these mature trees, ohia trees die, the area is just being taken over by guava, and we're not seeing any or very little, if any, recruitment by seedlings. This gives you a kind of a better idea about the dynamics in these lower plots, lower elevation plots. Ohia consists 62% of all the stems, 77% of all the basal area, which is a good proxy for biomass. So almost 80% of the biomass, the carbon mass of these forests is made up by ohia. In these lowland areas, if we were to lose ohia in these areas, we'd have this co-dominated, or these sites co-dominated by natives and non-natives, but the forest will be guaranteed much smaller and more depauperate in terms of native diversity. In contrast, when we look at above 3,000 feet or so, we see that even where we have ohia dying, at least we have native species filling in the gaps. And we see that here. Same story with ohia's dominance and its importance in the forest. 64% of the stems and almost 70% of the basal area in these forests and biomass of these forests is made up by ohia. But if we were to lose ohia in these upper elevation forests, at least what would be replacing would be native species. And so that's a good thing, even in the event of complete ohia stand collapse. I'm gonna skip over this stuff and just get real quick back to some things that confirm what Ryan was talking about in terms of fences. Our work on the ground is showing this exact same thing that he's seeing, is where we have high ungulate activity, we have mortality of ohia. Where we have low pig activity, usually in areas where we have fencing, we have much lower rates of annual mortality of ohia. And so I really want to emphasize this, because when we're talking about rod, we need to be talking about fences. We need to be talking about management. And right now, the only clear, effective form of management that we have for controlling rod, for keeping our ohia trees around us from dying, is fencing. And ungulate removal, obviously. And I just want to emphasize that, because obviously that's a touchy subject in Hawaii. And it can be uncomfortable to perform that kind of outreach, but it is critical, because it's the only tool that exists right now to control the spread of ceratocystis induced mortality. And I just want to challenge folks to kind of wrap their heads around this, to figure out how can we message this so that people understand as clearly as possible what we need to do to save our ohia trees, if people want to do that. And so that's just on us. And I want us to face that with bravery and courage. And when we're dealing with people who bump up against that and want to contradict this, I want you all to have the ammunition and the facts and the evidence to say, hey, listen, if we care about ohia, this is what we need to be doing. And that's pretty much it. So that's, I think, all I wanted to share with you all today. And I certainly hope there's time for questions, because I'd be happy to answer anything. Thanks.
Yeah, great, Flint. If you can stop sharing your screen, I will share with you some stuff that was in the chat box that rode through. Okay. I think one question came through on, what do you believe the theory is on why there's higher mortality in older stands or in older substrate?
So we don't quite understand that. It could be a few factors going on. There's the idea that perhaps some of these older, taller trees are taller, and so maybe they're catching more of the wind dispersed frass. Maybe they're more easily wounded. One hypothesis that I have, especially on these younger flows, is the fact that they don't get a lot of ungulate traffic. You know, we're talking historic flows. It's rocky. There's not a lot of soil. There aren't a lot of things for pigs to eat, for instance, in the soil. There aren't a lot of worms in a lot of cases. But once you kick in, it's amazing. Once you kick from the historic flows to these older flows, and that pivot point is at about between 200 and 300 years in age. You see more soil development, and you see a lot more mortality, and you can see them right next to each other where that's happening. And I have to believe part of that is ungulate activity and impact and the spread of the disease that way.
Great. Another question that was asked, are some of the plots fenced and some not fenced, or, you know, all this, your plot network?
Oh,
or anything?
Yeah. And so we definitely have plots that are fenced, that run along fence lines that are, we have paired plots that are in the unfenced area and paired plots that are in the fenced, kind of analogous to what Ryan was showing with some of his fence line comparisons. And we're seeing similar things, but I have to say, I think for the ungulate impact work and looking at mortality, our scale of resolution, I think, is a little too fine, because we'll have plots set up and we'll have a lot of mortality just outside the plot in a unfenced area where there's a lot of ungulate, and we'll get the sense that we're kind of not capturing that mortality. In the same areas where Ryan has his, these are some of the same areas where Ryan has his imagery from. He's seeing it because he's picking up things at a much larger scale. And so that's been an interesting thing to learn, that our sampling scale may be, in some instances, missing that impact in terms of the high mortality in the ungulate active areas versus the lower activity areas or the no activity areas. I hope that makes sense.
Yeah, great. If there's anyone else that has any questions for Flint, feel free to put it in the chat box, or if not, message one of us or message Flint himself, and I'm sure he will get back to you. Yeah, and
one more from Jeff.
Oh, sure, Jeff, sorry.
Right on.
I think he commented, but might be important for public to understand that even though Juliohea equals other background causes, is it on top of those other causes? You know, versus rust or other type of, I guess, diseases that you could find across the landscape?
Wait, I just want to understand completely the question. So is the Juliohea mortality that we have in those plots, is that on top of the background causes? Was that the question?
Yes. So
what we did in that analysis was if we had Juliohea present and confirmed, then we separated that out as its own category. And the one weakness in that data set is just we don't have as many Juliohea only plots as we wish we had. We only have, I think we have a dozen, which is in a data set of 250 plots is not that much, unfortunately. But based on those plots, those are the mortality rates that we're seeing. And those plots are scattered across the Big Island, so there is some spatial variation, which is good. But no, when in terms of the no ceratocystis plots, well then those are plots that we have no evidence at all, and we've tested the trees that have died in those areas. We have no evidence that ceratocystis was ever there. And those include plots that are within the national park that JB was describing, that we saw trees dying. We thought, oh wow, this looks like leucohea. And it certainly wasn't. And then when we follow those plots over time, we say, okay, well, there was an episode of mortality, but that's it. We're not seeing anything more, which is a good thing. That monitoring is showing that the trees aren't continuing to die. There was some episode, something was killing them, and then now they're in this pretty low background of mortality, or no mortality. You can see, I know I breezed through, but we have a lot of plots where we had absolutely no mortality, even in leucohea plots that had a dead tree from leucohea. Had plenty of plots where we showed no more mortality. Unfortunately, we had a lot of plots that were showing dramatic mortality after that too. So sorry, that's a long answer to that question. My apologies.
That's okay. I think that was the last question that was in the box, and just want to say thank you, Flint. Another thing that Flint mentioned was kind of, you know, if us as outreach folks can wrap our head around the fencing messaging and you know, taking the data from what we have and using that as support, right? And so if you folks are interested, we are going to be starting some strategy calls on our outreach working group calls. So I don't know if you folks are on that list, but if you are interested, please email me, and we will be meeting next week, Tuesday, to start discussing some of that.
And again, I'm not just a flat out advocate for fencing, and I'm certainly not a pig hater or a hunter hater by any means. I just want to make it clear to all of you that that's the only management solution that we have in our toolbox that really works.
Nice. Thank you, Flint. Thank you, Amber.